As you've probably seen from the title of this video, today we're going to be taking a look at a USA TSTST problem. TSTST stands for Team Selection Test, which is the selection test used to select people for the team selection test. So the reason I decided to share this problem with you guys here today and make this video was, well, I was doing this problem earlier, and I found quite a simple solution. It was simple in the concepts it was using, though quite lengthy. And I was looking up the model solution, which I only found one of. But that solution was short, but it made use of a lot of advanced concepts like inversion and projective geometry, which I'm not a big fan of. I like more simple concepts that just more contrarian in a sense. So I wanted to share my solution here with you guys today. Alright, so let's go through the problem setup. We have a triangle ABC. We can draw its incircle and incenter I. The incircle's points of tangencies are D, E, and F. We have the circumcircle. We have the midpoint of BC as M. Okay, so far all quite rudimentary setup. And then, now it's where it starts to get into the real thing. We have the line FE. We drop a perpendicular down from D, intersects at P. And then we draw AP, and it intersects the circumcircle at G. We draw IP, it intersects the circumcircle at Q. And the problem asks us to prove that D is the incenter of triangle MGQ. Okay, so let's recall some incenter properties. If we just have a triangle XYZ and its incenter I, well, we know that the incenter lies on the angle bisectors of all three of its angles. But if we look at this figure here, for example, if we were to find the angle bisector of GQM or QGM and prove that that intersects D, that wouldn't be really nice because it's quite difficult to find something like that. So maybe we should look for an alternative definition of the incenter. So if we can recall here, we have, first of all, we can draw the angle bisector from X here, and we know that this intersects the circle at a point N that is the midpoint of the minor arc YZ. And we also know that the incenter lies on the circle that is centered at N and has radius NY, NZ, and I. So that is a basic property of the incenter, in case you didn't know. And so we're going to use this property here today to prove that D is actually the incenter. And our claim is that if we can show that the circumcircle, first of all, we want to show that D lies on the angle bisector of YXZ, which in this case is QMG. So let's write that down first. Step 1, we want to show that DM, which is actually just BC bisects the angle QMG. Okay, that's our first step. And our second step is related to the circle. So we claim that this is equivalent to showing that the circumcircle or the circumcenter of triangle QDG lies on the angle bisector, which here is just the line BC. Well, if we think about it, that's a bit small, so let me just enlarge it here. If we think about it, the angle bisector of X and the perpendicular bisector of Y here, YZ, these two lines, they only intersect at one point, and this point just happens to be here. So in this case, the perpendicular bisector of QG and the perpendicular bisector or the angle bisector, which is BC here, only intersects at one point, so like somewhere over here. And this is actually just the center we want. So we just need to show that this is the center of QDG. And conversely, it just means we want to show that the circumcenter of QDG lies on the line BC. So 2 is to show that the circumcenter of QDG lies on BC. So if we prove these two statements, 1 and 2, then we have effectively shown that D is the incenter of the triangle, which is exactly what we wanted to show, because we have just explained that 1 and 2 are the sufficient conditions to show that D is the incenter. So now we can work on proving these two. So let's start with the first condition. The first condition asks us to find, or rather asks us to prove that QMB, this angle, is equal to BMG, this angle. Well, here actually comes the first major leap, in which we actually have to see a very key point in order to actually continue and proceed with the problem. And so the key observation, or rather more of a guess, is that if we define T as the midpoint of minor arc BC and S as the midpoint of major arc BC, our hypothesis is that QDT, like that, QDT is collinear and GDS is also collinear. So how do we make this observation? Well, one thing is, as we'll find out later, this observation actually helps a lot to prove our 1 and 2. And the second motivation for this observation is to just draw a nice figure and make guesses. You just trace out QD and see that, oh, maybe this intersects there. Alright, so now let's see how these two conditions can actually help us to prove our two statements. So the first statement we want to prove is that QMB is equal to BMG. Let me just quickly write that here, so because this is a bit more vague, so we can make it a bit more practical. We want to show that this angle is equal to BMG. So let's say that QDT and GDS are indeed all collinear. And here we can make the observation that if we look at GDMT, we have that DMT, this is perpendicular because, well, T is a midpoint and M is also the midpoint. And since S and T are opposite, they're the diameter, SGT is also a right angle, which is the same as DGT. This means that the 4 points DGTM are actually concyclic. Let me just erase this so we can see a bit more clearly. Oh, I didn't erase that. That's nice. So we know that the points DMTG are actually concyclic. So now if we want to find the angle BMG, which is actually equal to DMG, and that is equal to DTG, so we have that our angle DMG is equal to DTG. Well, similarly, up here, we have that the points, since Q or GDS are collinear, we have that the points Q, D, M, and S are actually also concyclic. So our angle QMD is just equal to the angle QSD. So now we just want to show that these two angles are actually the same. But we know that SDG are collinear and DTQ are collinear. So if we extend this, we see that these two angles are actually the same because they just correspond to this arc QG. Therefore, if we prove our assumption, then we have proven our first condition, which is that BC bisects angle QMG. So let me erase this stuff and hopefully not T. Oh, that's very nice. So actually, let me write that down here so we don't forget later. Our hypothesis is that GDS are collinear and also that QDT is collinear as well. So let's box this here. Okay, so if we show that this is true, we have already finished the first condition. So now let's see if this can also help us tick off the second condition. Well, here, if we have, let's just take a look at QDT first. So if QDT is collinear, then we have that, oops, I don't have the right color, give me a second. We have that line DQ actually bisects the angle BQC, and the reason being QT bisects this angle because T is the midpoint of the arc, and so since they're collinear, this thing bisects the angle. And by angle bisector theorem, we have that QB over QC is equal to BD over DC. Okay, and similarly on the other side, we can do the same thing and show that angle, or DG, bisects angle BGC, and so that GB over GC is equal to BD over DC. Okay, so by the way, these two expressions literally mean the same thing, so I'm just going to combine them into one, GB over GC. And let's erase the second one. And so what's interesting about this is that if we recall that we have 2 points, let's say X and Y, and if we can recall the locus of points such that the locus of points Z such that XZ over ZY is constant is actually a circle with the center somewhere here. So this is a well-known fact, and I think it's related to Apollonian circles, but anyways, this is a well-known fact and you can experiment this for yourself, but this is the result here. And since we have QB over QC equals BD over DC equals GB over GC, if we look at the points, I have the wrong color again. If we look at the points Q, D, and G, they are actually on the Apollonian circle. If we have X be B and Y be C, since the three ratios are constant, they three lie on an Apollonian circle. And we know that the center of the Apollonian circle lies on BC. And that is exactly what we want, because this point is the circumcenter of QDG, and this lies on BC. So that is exactly our second-ish condition here. Okay, so that's pretty cool because we have shown that if we prove our hypothesis, then all of our conditions will hold true and we have proved our problem. So now instead of having to deal with the nasty incenters, we actually only have these two collinear conditions to prove now. And we can actually prove them one by one. So let's start with GDS. To prove that GDS are collinear, we can actually take a look at a pair of similar triangles here. So if we I have the wrong color for the third time, and so let's look at these angles. This is perpendicular, by the way. So angle EFD is equal to angle EDC by the tangent C, and we also know that angle EDC, since this is isosceles, angle EDC is 90 degrees minus C over 2. So this angle is 90 degrees minus C over 2, and this angle is C over 2. Similarly, this angle is 90 degrees minus B over 2, and this angle is B over 2. So if we think about it, we can think about it later, because we know that if we look at the triangle BID, this is B over 2. And so we have the triangle BID is similar to triangle, what should it be? It should be DEP. So if we think about it, we can actually rotate this triangle, or just we have to rotate and then flip it, but if we can transform this triangle down to this triangle, and we can transform the triangle FPD in the same way down to the triangle IDC. And after we transform, let's just say we do these transformations, and then the side length, and let me just draw this down here. So this is point I, this is point B, this is point C. So we have transformed both of these down here. So we need to look at the ratio here. And well, we have that we shifted the length FP to the length, by the way this is D, we went from FP to ID for this triangle, and for the other triangle we went from PE to ID. So for the bigger triangle we transformed it a bit less, and for the smaller triangle we scaled it up a bit more. So the scale change ratio here is PE over FD, because well, we can just take the ratio of these two things. So we have that P over, oh sorry, this should be FP. P over FP looks like this. And they also have the common PD line, and under this transformation, for example with the first one, I kind of need some space. With the first one, the line PD goes to BD. And for the second one, the line PD, sorry, the first one should transform over to CD, and PD goes to BD for the second one. And if we take the ratio of these transformations again, as we've taken the ratios over there, we have that this should be equal to BD over CD. Or sorry, I mean CD over BD. I keep messing up the ups and downs. Okay, so actually let's write this a bit nicer. If we write this a bit nicer, we get that PF over PE is equal to DB over DC. So if we visualize this, it tells us that this ratio to this ratio is this ratio to this ratio. So that is pretty nice, because with this piece of information we can actually now prove something about GDS being collinear. Okay, and what can we actually do? So we can keep this relation and we can erase all this. So we can recall that since the line A, P, and G, or the 3 points A, P, and G are collinear, we can use some angle relations there. Specifically, we look at the triangle AFE. Let me draw it here so we can see it a bit more clearly. And we have the P comes over here. So by the, I think this is law of sines. This is a result from law of sines. That's pretty convenient to memorize. But let's say this is alpha and this is beta. Then we have the sine alpha over sine beta is equal to PF over PE times AE over AF. Okay, so why is this useful? Well, let's look at this, and then if we apply it here, this is alpha, this is beta, but we also know something else about sine alpha over sine beta. Since they're both inscribed angles in this big circle, sine alpha over sine beta is actually just, this is just this line over this line. So this is actually just equal to GD over GC. Oops. So we have that GD over GC is equal to whatever this thing is. But we can actually simplify the right hand side a bit. First of all, since AE and AF are both tangents, they're the same. So this thing it just cancels out. And we know that PF over PE is equal to DB over DC. So we have that GD over GC is equal to DB over DC. Well, doesn't this look very familiar? Because this is the Apollonian relationship we were just talking about. So yes, this actually gives us the Apollonian relationship we wanted, but it'd be nicer if we could just transform it back into the simple relation that GDS is collinear. And how do we do that? Well, since GD over wait, I think I wrote something wrong. Oh yeah, this should be GB. Give me a second. GB. So since GB over GC is equal to DB over DC, we have that this angle or DG bisects this angle. And since S is the midpoint, that means that GDS are indeed collinear. So we have actually proved this first one, which is nice because now we're over 50% of the way done, and we only have one last thing left to prove that QDT is collinear. Okay, so to prove that QDT is collinear, we can actually use what's called the method of false positioning, which in my opinion is really cool. How this works is that we define a new point, Q prime, to be TD intersects the circumcircle of ABC. So we want to show that Q prime is just Q because Q prime TD are collinear. So we want to show that Q prime equals Q. And so what can we do about this point Q prime? Because of space issues, I'll just cover my Q here and call it Q prime. And we know that Q prime DT are actually collinear. So here we will go for a bit of a similarity, but before that, let me erase some of this to make space for some of our observations. Let's look at the similarity between the circumcircle of AFIE and circumcircle of ABC. So let me just draw the circumcircle of AFIE first. Hey, that's a pretty good circle. So if we notice, there's actually some kind of similarity between these two circles, or these two entire structures in a sense. Well, first of all, it looks like FE and BC are kind of similar. Well, that is true because FE is subtended by the arc, by the angle A, and BC is also subtended by the angle A with respect to the circle. So FE and BC are actually quote-unquote similar. And since I is the midpoint of FE and T is the midpoint of BC, I also corresponds to T. Okay, so finally, from this relation, we have that PF over PE is equal to DB over DC, which means that P lies along this line just as far, ratio-wise, as D lies along this line. So that means that P and D correspond under this similarity. But what's interesting is that not only is this a similarity, it is actually also a spiral similarity that's centered at Q prime, and we will show that in a moment. So my claim, or our claim, is that we can rotate the circle in a spiral similarity fashion to get this new circle with all the points corresponding. So to prove that, we essentially just have to prove that BQ prime F is and CQ prime F are actually equal, like the angles are equal and the triangles are similar. So why is that? Because if we rotate B Q prime F, if we rotate, we have B go through the spiral similarity, go to Q F, and we have C go through the spiral similarity, go to E, then we actually just have the entire figure go through the spiral similarity. But before we talk too much, let's first prove that this is actually indeed true. And so how are we going to do that? Let's first see that this angle is subtended by the arc Q prime A, and this angle is also subtended by the arc Q prime A. They're the exact same. And to prove that these two triangles are similar, we can actually just use SAS by looking at these two side length ratios. Specifically, we want to show that BQ prime over BF is equal to CQ prime over CE. But since BF is tangent to this incircle, BF is actually just equal to BD. So let me just write this as BD. Similarly, CE is actually just equal to CD. So we have that this relation is just equal to the relation that BQ prime over CQ prime is equal to BD over CD. But since we define Q prime as the ideal point, which is that it is collinear with D and T, then we have that this relation is obviously true, because this is the Apollonian relationship we were just talking about, and this is true because Q prime dt is the angle bisector of BQ prime C. Okay, so we know that these two triangles are actually similar. So, since these two triangles are similar, we can actually just perform a spiral similarity from Q prime FB to Q prime EC. And that spiral similarity will map B to F, C to E, and hence it will map BC to FE. And since D and P correspond on these two line segments, D will map to P, and similarly T prime will map to I. Okay, so now we know that D, T, and Q prime lie on the same line, and since D, T, and Q prime in this spiral similarity, under the spiral similarity, correspond to I, P, and Q prime, they must also lie on the same line, which means that I, P, Q prime must be collinear. But since we defined Q prime to be on circle ABC, for I, P, Q prime to be collinear means that Q prime must be equal to Q. Hence, we have proved that Q prime is indeed equal to Q, and so we have shown that Q, D, T are collinear. So, now we have shown both of our original claims, one that GDS is collinear, and one that QDT is collinear. And we have also shown before that these two successfully imply these two conditions, which successfully implies that D is the incenter. And we are done with the problem. So, what is the takeaway here? Well, the takeaway is for this problem is to work backwards. For most cases, you want to work backwards a lot. In some cases, things are a bit different. But in this case, we have to look at the end goal, which is to show this incenter. And then we work backwards from there to see how we can actually prove this statement. Because if you only work forwards, you have all these conditions, you derive all these things, but then you may be deriving 100 things, but only like 2 of them are useful for your actual thing you're trying to prove. So we want to work backwards to see what conditions we actually need, and then we don't need to do this, we'll need to do this, we can go straight to the answer. And so this is a great example of how we work backwards here by seeing that if we want D to be the incenter, that is equivalent to these 2 conditions. So we worked backwards, and then we see that these 2 conditions, if we work backwards, is actually equal to this condition. And then from there on, we can prove that these 2 are true, which since these are all bijective, we can just go all the way back and prove our original statement is true.